This video is going to be part of a series of videos on confounding I'm going to do, and I'm going to break it down into three. This one's just going to be a broad overview of confounding. Then there's going to be another one where I talk about how to detect confounding, and a third one about how to control it. It's a super broad topic that's probably the most important topic in epidemiology, so I'll do my best to do it justice. Yeah, it's basically like most of the methodologies involved in epidemiology, whether it's analysis or study design, is mostly around trying to mitigate this. So it's a very broad topic. So just a broad definition, confounding is when a variable distorts the relationship of interest. So we're interested in the relationship between this exposure and the outcome, but this relationship is being distorted by this third variable, a confounder. And for something to be a confounder, it needs to meet three criteria. So it needs to be causally related to the exposure, it needs to be causally related to the outcome, and it can't be an intermediate on the path from the exposure to the outcome. Some texts you'll see will say that the confounder and the exposure only need to be associated. Note that this doesn't apply to the confounder and the outcome. And what that means is, well, this is a causal relationship, saying the confounder is exerting an effect on the exposure. An example of it just being an association is something like if we're interested in the mortality rate varying by country, and we don't take into account the age distribution of those countries, we might see a very high mortality rate in countries like America and like in Canada, developed countries, but that is part of that is because the age distribution in those countries is there's a lot of old people, and basically mortality rate is higher in old people as a whole, so it starts to distort this mortality rate. And this is an association only because being old doesn't cause you to live in this country, and it's more just an association rather than anything causal. And why confounding is so important is because when it's uncontrolled, it's very difficult to anticipate what it's going to do to your exposure outcome relationship. And that's what makes it scary, because if you see some relationship that is monumental and you're so excited that you found a relationship between this exposure and outcome, you're going to spend a lot of time defending the idea that it's not due to some third factor. So yeah. Positive confounding is when the presence of this confounder causes this relationship to be amplified between the exposure and outcome. And that happens when the confounder and the exposure and the outcome have a similar relationship. So let's just say the confounder and the exposure have a positive relationship. So as the confounder goes up, the exposure goes up. And this is also the case with the exposure and the outcome. They're positively related. Then the presence of this confounder is going to amplify this exposure-outcome relationship. The opposite is negative confounding, and that's when the presence of this confounder attenuates the exposure-outcome relationship. So this happens when they're in opposite directions. So let's just say the confounder and the exposure have a negative relationship, so when one goes up, the other goes down. And the exposure and the outcome have a positive relationship. When exposure goes up, outcome goes up. They're going to offset each other, and the presence of the confounder is going to attenuate this relationship, so make it seem less strong. And qualitative confounding is when what I just described here, the attenuating effect is so strong that it causes the relationship to change direction. So when the confounder is controlled for, we see a exposure outcome relationship that's, say, positive, and when it's not controlled for, we see that it's negative. So this confounder is having such an effect on the relationship that it's changing the sign qualitatively from a positive to a negative relationship. And this happens when these two have a negative relationship and these two have a positive relationship, or vice versa, and it is an extreme magnitude of difference in addition to difference in direction. So for those of you that are visual learners, I thought I would bring out my population diagrams again, just to kind of illustrate visually what confounding looks like in a population. So if we're investigating, if our exposure outcome relationship of interest is a fatty diet and liver disease, and we have this fatty diet group and non-fatty diet group, and we're measuring liver disease in the two groups, we're functioning under this assumption that the two groups are exchangeable. And that's the case typically in a randomized control trial because we randomly assigned a healthy diet and fatty diet. But in the real world, people self-assign their exposure status. They choose a healthy diet or choose a fatty diet, and that doesn't necessarily happen at random. So those who choose a fatty diet might have some third variable that is related to that choice, and that becomes a problem if that third variable is also related to the outcome. So my potential confounder here is alcohol, where it might not be a causal relationship, but those who choose a fatty diet might also be more likely to consume alcohol, while those who are more health conscious and choose a healthy diet might be less likely to choose alcohol. And that probably would have been better to write as an association rather than something causal. But like I said before, that it only really needs to be an association, so that can still be a confounder. So now we have the blue people that are those who consume a lot of alcohol, and these black people that are the ones who don't consume a lot of alcohol. And basically, we can see that among the fatty diet group, this prevalence of high alcohol consumption is higher and likely to distort this relationship. And yeah, this is different from selection bias in the sense that this association is real among these fatty people who have a fatty diet. They really do have a higher likelihood to engage in alcohol consumption. In this example, it would be selection bias if somehow the way we were admitting people to the study caused the distribution of alcohol consumption in the two groups to not represent what they are in the real population. And that brings me to this idea of exchangeability, where in order to really isolate the relationship between fatty diet and healthy diet, we want our two groups to be the same in every way except for their diet. And we can see here that that's not the case, because not only do they differ by diet, but they also differ by alcohol consumption. So if we were to switch the fatty diet and the healthy diet group, that would lead to very different conclusions. And that's the idea of exchangeability of the two groups. And just to illustrate how randomization takes care of that, like I said before, a confounder needs to be related to the exposure and the outcome. Randomization essentially breaks down the relationship between the confounder and the exposure, because since we are deciding what their exposure status is, there's no chance for it to be related to anything really, or really related to any unmeasured confounder, because we forced ideally the only way these two groups to be different as their diet status, because they didn't self-assign themselves. It had no chance to be related to this confounder. And just to illustrate that visually, before we had our two groups that are visually different, but if we jumbled them and shuffled them into this group and randomly assigned them left and right, then we're more like, this is an extreme example where it worked out nicely, but we usually have a lot more people than this, and we end up with a more balanced distribution. And although this group has 6 and this group has 5, you get the point. They're essentially exchangeable, where you could switch you could switch the diet of the two groups and probably come to a similar conclusion. So DAGs, or directed acyclic graphs, are a really popular way to identify confounders. So you start out by just kind of graphically mapping the relationship between things in that are part of your relationship here. So if we're interested in smoking and lung cancer, and we think occupation is involved, we would first put occupation in the diagram and then try and justify how it might be related to other things. Is smoking causing occupation? Is lung cancer causing occupation? We can justify that there's certain occupations where smoking is more likely. Maybe you weren't a smoker, but you go into an occupation where smoking might be more common, such as like construction or something, and then you might engage in it for the social factor, and in that way occupation might lead you to smoke more or decide to start smoking. Might be a bit of a stretch, but it's not unheard of. And occupation could be related to lung cancer in the sense that you might have certain occupational exposures that can cause lung cancer if you're working around chemicals. And by that thought process, we were able to arrive at the idea that occupation might be a confounder. So another more complicated example that I couldn't come up with a real example because I made it too complex. So we just have X, our exposure, and Y, our outcome, and these other variables we assume are involved, and we come up with this complicated interrelationship. And now we can search for confounders. So like I said before, the confounder needs to be causally related to both the exposure and the outcome. So it's basically just these two. This one's only related to the outcome. This one's only related to the outcome. Only related to the exposure. Only related to the exposure. This one is directly related to the outcome and the exposure. And this one, although it's indirect, is technically causally related, although it goes through Z2 here to the exposure, or to the to the exposure, and through Z4 here to the outcome. So by using this DAG, we were able to identify these two confounders. I wanted to talk about confounding by indication, which is a very specific kind of confounding that tends to show up in clinical epi, and it's really common when the exposure is treatment and the outcome is mortality. And the reason for that is because the severity of the illness often informs what treatment the doctor decides to give them. They might give someone a much more invasive and drastic treatment if they have a more severe disease, where if their disease isn't that severe, they might weigh the consequences of such an invasive procedure and decide it wouldn't be worth subjecting them to that risk if they only have mild disease. And also, it's kind of obvious the severity of your illness is related to mortality. So in that way, disease severity is a confounder. It's related to the treatment you get and the mortality. And a huge caveat here is that we're not randomly assigning to treatment. This is a situation where the doctor decides what treatment is called for. And just to kind of illustrate confounding by indication, this is just an example from my research where it's an observational study comparing mortality among two treatments for heart disease, infective endocarditis. So it's either antibiotics given to non-severe cases or valve replacement given to very severe cases, and the doctor is choosing who gets what, probably based on the severity of the disease and other kind of prognostic factors like frailty and stuff. So you can see among the valve replacement group, the blue people, those with severe heart disease, it's much more common in the valve replacement group than the antibiotics group. And this might lead you to conclude that mortality is much higher in valve replacement. You might conclude that it's an ineffective treatment, but you need to consider the fact that those who were given that treatment were already doing pretty poorly, so their mortality rate would have been higher regardless of whether they got the treatment or not. And the last thing I want to talk about is the minimally sufficient set, and this was in my DAG video as well. And it's just the idea that you might be able to control all of the confounding in or XY relationship without having to control everything that is a confounder in the DAG. So here we have three confounders, Z1, Z2, and Z3. And you might think we need to control all three. Throwing them all in the model here is how I'm representing that, and deleting them is how I'm representing that they've been controlled. And that would control the confounding. But this could be problematic because it might be expensive to collect data on all three. If we're matching, you might not be able to find matched pairs. So there's a lot of reasons it might be better to try and find two that you're able to control all the confounding. So if we control for Z1 and Z2 and put those in the model, even though Z3 was a confounder, we've blocked its path to X, so we've eliminated all the confounding in this relationship without having to control all the confounders. And that's just the idea of the minimally sufficient set. And lastly, even if we have a confounded relationship, here it's been observed that race is related to hypertension, and that doesn't actually have much of a biological basis. It's more due to socioeconomic status, so access to healthy food or salty food and stuff like that, and healthcare in general. So it's these inequalities that is responsible for this relationship. So even though that's a confounded relationship, this race hypertension relationship, it's still useful in the sense that We could provide more screening and prevention to certain individuals that are at a higher risk, even though it isn't the race that's causing them to be at a higher risk. It's more this distorting, confounding variable, but still offering targeted screening and prevention to certain individuals. We're able to help people, even though we based this decision off a confounded relationship.